considerably. So I'm going to start talking through. We've worked with some of these kinds of symmetry before. We've worked with y-axis symmetry bunches. That would be when we had our line symmetry, and it could reflect across that y-axis. Things that we have seen that have y symmetry would be stuff that's like, you know, a parabola. Y-axis symmetry. Y-axis symmetry is also called being even. So if it asks us to look at something as even or not, y-axis symmetry is also called being even. X-axis symmetry is not something we see super duper frequently because it does require something to pretty much not be a function. Because that would be something like the one we did yesterday where we had our x equals y squared like this. That has x-axis symmetry. It reflects over that x-axis and lines back up with itself. That one doesn't have another name. It's not super common. And origin symmetry is another one of those things we've seen before. Origin symmetry is going to be like our point symmetry. It means it could rotate around the origin. It would make a decent spinner. So I could rotate this and have it line back up. I could spin it. Or I could balance it on my finger and it would balance. Parabola I could not balance on my finger. It would go and fall. Something like a line or a cube or anything where we have that kind of balance, I could find my balance point and it would balance. Or I could, if I'm very good, spin it and it would line back up. Origin symmetry also has its own special name. Origin symmetry, line symmetry, y-axis is even. Origin symmetry, odd. So if we're looking at things are even or odd, we're looking at does it have y-axis symmetry or does it have origin symmetry?
And then x-axis could be any.
X-axis doesn't have a special name for it because it's not super duper common.
Okay.
Because for the most part, for something to have x-axis symmetry, it's not going to be a function. So it would be when we have, we're going to look at one that has it, so we'll see an example. Because we're going to do these tests. So a lot of times what we're doing is we're seeing if we get the exact same answer when we change one sign. So for our y-axis symmetry, we should have the same value for when x is 2, x negative 2 should have the exact same y value. So if I replace x with minus x, I should get the exact same y value because they line up over here. So if we replace x with the opposite of x and get the exact same answer, we have y-axis symmetry. Same thing with our x-axis symmetry. But this time, since we're looking at where it's flipping across the x-axis, it would be that an x of 2 could give me a y of 4 or a y of negative 4. I could switch that sign. So if my y replaces, then we would have our x-axis symmetry. For origin symmetry, it would have to do both. We're going to place x with minus x and replace y with minus y. Because that would make it switch basically to the other quadrant, diagonally. So points in quadrant 1, like if it was going through point 1, 1, that would rotate around to negative 1, negative 1. Or 2, 4 would become negative 2, negative 4. So we're going to test this by substituting in opposite of x or opposite of y. We need more time to write. I didn't want to rush us through this because I know there's a lot of words up here. A lot of stuff. Door? Any question? Okay. Just fiddling. It's all good. Fiddle away. If you ever need to fidget, I have a vast variety to choose from. Totally valid. Slugs, buttons, clickers, infinity cubes, all the things. I have bouncy bands for feet. All the things. So we're going to determine the kind of symmetry that these functions will have. I am probably just going to do one on a page, so I'm going to just copy this page. Paste. There we go. I'm just going to look at this left one first. I want to make sure we have plenty of space. So I'm just going to look at this left one. Because we want to test if this has our even symmetry or our y-axis symmetry. We're going to test if this has our x-axis symmetry. And we're going to test if it has origin symmetry. It is very rare for something to have more than one kind of symmetry, but it is not impossible. We will see one example of it today, because I want us to see what that means. So when we're looking for our y-axis symmetry to see if this is even, we're going to replace x with minus x to see if we get the exact same equation we started with. So this is our original equation. If I replace my x with minus x, and then simplify it. Those parentheses aren't doing me a dang bit of good. Nothing is happening over there. I don't have anything we need to multiply in. I don't have any powers I can put on it. That just says minus x equals minus y squared. So I replaced this x with minus x. Is this exactly the same as this?
No.
No. So this does not have y-axis symmetry. Nope. It's not the same. Doesn't count. Move on. Let's see about our x-axis symmetry. For this one, we're going to place our y with minus y. So we're going to have our x equals the opposite of minus y squared. I'm substituting it in place of the y right here. Can we simplify this?
Yeah.
What happens when I square a negative number?
Turns positive.
It turns positive. So if I square the opposite of y, I'm going to get back out exactly y. So this would become just our y. So the rest of it's going to stay the same. Our x equals the opposite of y squared. Is that exactly what we started with?
Yeah.
Yes. So this has x-axis symmetry. We're still going to test origin symmetry too. In that case, for origin, we do both. We switch our x with minus x, we switch our y with minus y, and see what happens. So we're going to switch our x out for a minus x. That is not how I write an x. There we go. I don't know why, but I started writing a 5. Switch our y out for minus y. And it's going to combine all the simplification stuff we've done. We've thought all of the processes before. We're just doing them both at the same time. The opposite of x, that nothing's really happening over here, so that's just going to stay minus x. And then we have our minus y squared. That's just going to become y squared. So do we get the exact same thing we started with?
No.
No. So this does not have origin symmetry. This has x-axis symmetry only. So when it says determine the type of symmetry, this has x-axis symmetry. Spelling is a suggestion, especially on the word symmetry. I always put way too many M's. Symmetry. It feels like too many M's. Even if it's just one, it feels like too many M's. Questions on our first one of these? Yes, Dave.
Why is it still squared like in the x-axis one?
Oop, sorry, I jumped pages on me. On the x-axis one, because even if I have minus y times itself, minus y times minus y, we get y squared.
Oh, okay.
Okay? Good question, good question. Okay, let's do another one. Fix my pages because they all decided to change orders on themselves for absolutely no reason. Never mind, I'm just gonna use it out of order and I'll just fix it later. All right, so we've got our y equals 1/4 x cubed. Ignore the fact that's on the right side of the page, just so we had plenty of space to do that one. So our next function is gonna be y equals 1/4 x cubed. We're gonna do those same tests. We wanna see if we have our y-axis symmetry. I'll do it in the same color. We have our y-axis symmetry. We have our x-axis symmetry. We'll have our origin symmetry. Those are the ones we're testing. It is entirely possible for something to have no symmetry. Absolutely a thing that can happen. So you might do all 3 tests and get no for everything. And that's valid. That doesn't mean you're wrong. Just because I know we tend to panic. So when we're looking at this one and we're going to test to see if we have our y-axis symmetry. Because my function's so far away, I'm going to write it over here too. So this was our y equals 1/4 x cubed. I'm just putting it over here because the way I have it zoomed in, I couldn't see it. So when we're looking for our y-axis symmetry, we're going to replace our x with a minus x. So we want to know if y equals 1/4 times minus x cubed is going to give me back that exact same function. So if we have minus x times minus x times minus x, are we going to wind up with a positive or a negative x?
Negative.
Negative. So this would be the exact same thing as if we had our 1/4 times minus x cubed. Or same thing as y equals negative 1/4 x cubed. Same thing. Either way, does it match what we started with? Nope. So we do not have y-axis symmetry here. Then we're going to do our x-axis symmetry. That's where we're going to replace our y with the negative y. So if we have y minus y equals 1/4 x cubed. Is anything going to change when I simplify it? Nope, there's nothing multiplying onto, there's no powers onto, there's nothing going on with this y. Genuinely no idea why I tried to write a 4 there. My brain's in a mood. So did we wind up with the exact same thing we started with? No. I mean, I could get to a y equals if that helps us. Like sometimes we could do that. Like I could put this back as to a y equals. We then get exactly what we had on the first one. That means the same thing. I could write it like this. Still doesn't match. We want to try and compare it with the originals. We need to see all the pieces. So then when we look at our origin symmetry, switching our y with a minus y, and our 1/4 x cubed with a minus x cubed. Well, we've simplified the minus y before. We just got left with our minus y. We've simplified our 1/4 minus x cubed before, and we got minus 1/4 x cubed. What do we notice?
They're both multiples.
They're both multiplied by -1. So if I get this back to a y equals, what do we get? 1/4 x cubed. Does that match what we started with? Yes. So this one has origin symmetry. I could use this one as a spinner. It's got origin symmetry, or you could just call it odd.
Oh, that's why it keeps.
Okay. Questions on this one? Cool. Let's do another one, another couple.
Oh.
Both up here.
Yes.
I am probably going to split these apart just because it makes it way easier to write it. Oops, sorry. So I'm going to do the left one, and we'll do the right one next. It's easier if I have a little bit more space to write up here. These aren't super like long problems. We just have to do the 3 options. So you can do them all in like single row if that works for your brain. But we're going to do our y-axis symmetry. We're going to test our x-axis symmetry. And we're going to test our origin symmetry. And I go slightly over the half page, so I'm just going to do them on 2 separate pages. So for our y-axis symmetry, that's when we're seeing if our x's could flip-flop over. So we want to know if we have our minus 3 and we take our minus x, squaring it, plus 4, if we're going to get the exact same thing as what we started with. Because if I take my minus x times my minus x, what do we get back? Positive x. So we're going to have our minus 3, and this minus x being squared is the exact same thing as if we just had x squared. It doesn't matter if I have x as negative 2, negative 2 times negative 2 is positive 4, or if I have x as positive 2, positive 2 times positive 2 is 4. Doesn't matter if x is positive or negative, I'm going to get the exact same answer either way. So does this have y-axis symmetry? Yep. So this one is also called even. It is an even function. We are still going to test for our x-axis and our origin symmetry. It is not super common, but it is possible. So for our x-axis symmetry, we want to know if we switch our sign on our y, if that's the exact same thing as our minus 3x squared plus 4. We substitute in a minus y. That's just going to give us minus y equals this thing. And it's probably easiest if we switch this back into a y equals instead of minus y equals, just so we can compare it. So I would divide everything by negative 1 or multiply everything by negative 1, whichever way works better for your brain. And that's going to give us our 3x squared minus 4. Is that exactly what we started with?
No.
Nope. So we do not have x-axis symmetry. And then our last one is our origin, where we get to do both. So we're going to have our minus y and our minus 3 minus x squared plus 4. I like to substitute everything in the parentheses right off the bat. It kind of lets us see all the pieces. You don't have to. If you can start out by doing your simplifying, that's totally fine with me. Just make sure we're checking. We know that when we have our minus x times minus x, we're getting our positive x squared. We've got our minus y equals negative 3x squared plus 4. Exactly what we had right here. So are we going to get back exactly what we started with? Like, you could absolutely finish it out. Finish it out by dividing or multiplying by negative 1. We get our positive 3x squared minus 4. Exactly what we got on our y-axis symmetry. Either way, it's a no. So if we spot it, especially if we spot it like this to see that these two things are exactly the same, sweet, totally cool. You don't got to finish it out. Totally fine. We're just seeing if it has the symmetry. So this only has our y-axis symmetry. just going to write it over here because it's really challenging for me to write it when it's on the other side. X squared plus y squared equals 4. And we want to see about our y-axis symmetry, our x-axis symmetry, and our origin symmetry. We're going to test all three. Just like we have been. So for our y-axis symmetry, we're going to replace our x with a minus x. So we're going to make this be minus x squared plus y squared equals 4. What happens?
The same.
It's exactly the same because minus x times minus x, we get a positive x squared. We get our positive x squared plus our y squared equals 4. So does this have y-axis symmetry?
Yes.
Yes. We get exactly what we started with. We'll do the same thing for our x-axis symmetry where we switch out our y. We're going to have our x squared plus the opposite of y squared equals 4. What happens on this one?
The same thing.
Same thing. We get our x squared plus y squared equals 4. Because again, minus y times minus y is going to give us a positive y squared. So this one also has x-axis symmetry. I wonder what happens with our origin symmetry. Well, let's take a peeky peek. So here we're going to do both. Minus x squared and our minus y squared. Well, what's going to happen there?
The same thing.
The same thing. Because minus x times minus x gives us positive x squared. And our minus y times minus y gives us positive y squared. So this also has origin symmetry. It has everything. Why? What shape is that?
I have no idea.
That's a circle.
Oh.
I say that would be a geometry thing. So I know it's been a little while since we've done some geometry. That's a circle with its center at the origin. Technically, radius too. We're going to talk about circles in a little bit. Okay. We'll be all right, I promise. Okay. Questions on our symmetry stuff? Because they're not super pleasant. They're not super long, but they're just finicky. Next thing we're going to talk about for today is we're going to talk about x and y intercepts. Those are going to be things we're asked to find. We've worked with these before, again. What is an x-intercept?
Where y equals 0.
Yeah, it's where y equals 0. It's when the graph crosses an H on the word graph crosses the x-axis. And we write our x-intercepts as a point. Whatever number we get is our x, and our y is 0. So when we're trying to solve that, when we know y is 0, we're going to substitute in 0 to find x. So for our x-intercept, we don't know x. We know our y 0. X can be anything. So what about for our y-intercept? That's going to be where x equals 0. it's very much the same kind of vibe. It's when the graph, or when a graph, crosses the y-axis. And again, we're going to write them as points. But this time I know my x is 0. So it's going to be 0 and then whatever value we get for y. Oops, that's not the button I meant. There we go. And we're going to find a couple of x and y intercepts to kind of practice this. We're going to start with something familiar, though.
Oh.
Starting with something like this. We've seen these kind of guys before. We've worked with quadratics. So if I want to find my y-intercept, what do we know about our y-intercept? X equals 0. So we would substitute in 0. So I would know this would be 0 squared plus 8 times 0 plus 7. So what's our y-intercept? 7, because this is the same thing as 0 plus 0 plus 7. So our y-intercept is going to happen at the point 0, 7. And in fact, for quadratics, it'll always be your c value over here. What about our x-axis, or our x-intercepts? How are we going to find them? Y equals 0. So for our x-intercepts, we know that y equals 0. So we're going to put 0 in for y. How do I figure out what x is? Factor it. This is a normal quadratic trying to solve it. Get down to where x equals. We need a pair of numbers that multiplies to make 7 and adds to make 8. 7 and 1. Those multiply to make 7, add to make 8. So our factored form here is going to be our x with a positive 7, x with a positive 1. If we don't have an a value, we can take the shortcut. If we have an a value, you've got to factor it properly. If we don't have a number in front of the x squared, we can do that. So what are our x-intercepts here? -7 and -1. So as intercepts, we write them as -7, 0. -1, 0. Okay. We can do the same kind of thing with any kind of function. We're going to do one more. This will be our last one for today. It's square rooty, but we can do this. We've got our y equals -2 square root of x plus 9 equals 10. So if we want to find our y-intercept, what do we need to do? Replace x with 0. So we know our y is going to be -2 square root of 0 plus 9, and then minus 10. Everything in here is a number. We can simplify this. We're going to have negative 2 square root 0 plus 9 gives me 9. What is the square root of 9?
3.
3. So we get our negative 2 times 3, giving us a negative 6. Minus 10, what's our y-intercept?
Negative.
Negative 16.
Negative.
Since we are looking at functions here and we've got a y equals, we can just take the positive root here. It's when we square root both sides of an equation that we would put our plus or minus in. Okay, so if we put the square root in, we put the plus or minus. If we're just looking at a number like this, we just look at the positive one. So our y-intercept here is going to be that 0, negative 16. Let's find our x-intercept here. That's where we're going to put our 0 in for y. And what do? Add 10 to both sides. We have 10 equals negative 2 square root x plus 9. Then what? Divide by negative 2. So then we have negative 5 equals square root x plus 9. Square both sides. 25 equals x plus 9. Subtract 9. 16. So our x-intercept would be at 16, 0. Okay? So finding x and y intercepts, we're just substituting in zeros. Okay? We can do that. This just has lots of little bitty details in them. So many. We have started in section 3.2. Today is not the 12th, today is the 11th.
What?
I would just had the date on it from last year still.